Okay, we're about to get started now with the Intel Generic Access Platform presentation. If you'd give a warm welcome to Ed Dylag and the rest of the crew from Intel, please.
Okay, great. Thanks everyone for joining us today. I think we've got a great panel up here. And I want you to mostly hear from that panel today, but I'm going to do a little bit of a brief intro and sort of set the stage for what we're going to talk about. So you might remember me from this very stage in Atlanta last year, and Matt Peterson. We were up here talking about something called GAP, or Generic Access Platform. And in a nutshell, GAP is a standardized modular enclosure to house next generation access nodes. And it's also a work item in an SCTE working group. So standardized, modular, next gen access, and part of a standards working group in SCTE. I'm going to leave it at that, and the panel will fill you in on some of the details here in a minute. So taking a look back at last year, essentially what I told you then is, or what we had then, was essentially a GAP proposal. Because at that time, at that point in time, that's as far as GAP had progressed. It was a concept. It was to a point where we could put forth a proposal for how you would implement this standardized modular node. And for those of you who are here and have really good memories, you might remember that I talked about a lid half that was, I was calling it an intelligent half. It had a base that was power and interface half. And I mentioned that, yeah, we envisioned that each half would be modular but different because of the different types of components that you need to deal with inside of these nodes. So let's take a look at how we've evolved the specification since then. Well, generally, we've evolved along those lines. We still envision the lid and the base being distinct, modular but distinct. We envision that the lid is going to be primarily for application modules, and that it will have an option for either a low-speed or a high-speed backplane. And one thing that has changed is we now are looking at compute as a module, whereas last year I was talking about compute as part of the high-speed backplane. And I think compute as a module makes a lot more sense for a lot of reasons. So I think we got that one right in the work group. And yes, the base is primarily for power and interface, but there's also an opportunity to put application modules in that half if you needed to. And that would apply for, you know, like optical use cases as an example, or possibly wireless, where you have to connect to an external antenna. So generally, we've evolved along those lines, along the lines of the proposal we put forth last year. A couple other things have changed. The work group now consists of over 100 individuals, and we've made a tremendous amount of progress on the specification itself. And I think now we are very much multi-access. You know, we've always talked about the fact that one of the goals with GAP is to house different types of access technologies. But now I think we've got the representatives in the work group who have experience in those areas, like wireless, like optical, and they're bringing their expertise to the specification as well. So again, tremendous progress. What we've also progressed to is we've progressed to a prototype. And a subset of the companies that are up here with me on stage today, got together and decided to build an actual functional prototype of a GAP module. And we did just that. And you can see this on the show floor in 3 different spots, which I will talk about after the panel session. I'll tell you exactly where you can go see these. But what we put together is essentially a DAA node that has fully functional RF modules, power supplies. It's got a high-speed backplane, PCI Express backplane. It has an RPD module, and it has an Intel Xeon D-based compute module. And the companies that you see on the bottom came together to put that prototype together. So talk about a multi-vendor effort coming together. So it's really great to see. With that, I'm going to basically switch gears here and ask some questions of our panel. So first of all, who do we have up here? So we've got Matt Peterson, who's VP of Access Architecture at Charter. We've got Elad Blatt, who is Chief Strategy and Business Development Officer at Silicom. We've got George Goncalves from AOI, who's a Business Development Director there. We've got Sean Welsh from Cisco, who's Vice President and General Manager of Cable Access. And last but not least, we've got Jay Lee, who's the CTO of ATX. So I'm going to start with Matt. So Matt, why GAP? What problems did you guys see, or do you see, that GAP can help solve?
Yeah, I think a lot of problems that we've encountered over the last couple of years is anytime we have new technologies that we want to go and deploy, companies come with us with that new technology. They have a new node housing for that technology. And new companies that are trying to make an entrance into cable really struggle on getting the enclosure, the thermals, the powering right, and being able to meet like IP68 specifications. It seems like they really struggled with that. So having a standardized node housing, having a platform where get the companies out of focusing on the actual enclosure itself, but more so on what they really do well. Have them focus on the technologies that could actually get plugged into that, and really reduce the development cycles for us and help us increase our deployment times.
Okay, all right. So Jay, I'm going to go all the way to the other end. So Jay from ATX, so along those lines, what is the GAP specification, what is it specifying and what is it not specifying?
Sure. So along the lines of what Matt was saying, it's important that we define an environment where application modules can be plugged into this platform. So key elements that we're defining are the housing. Lots of design details go into the housing, the associated thermal profile with the housing, as well as all of the electromechanical interfaces for application modules to plug into the platform. And then the last piece is the management infrastructure within the platform itself.
Okay, so
what's it not going to define is the functionality of any of the modules. So that's the part that's going to be left to vendor ingenuity.
Okay. Okay, so no functionality. That's, as you said, it could, whatever tomorrow's access technology is. But Matt, maybe you can fill us in. What are some of the top use cases that you envision?
Yeah, some of the technologies that I envision, you could have an RMD, sort of a remote MAC-PHY device as a module being plugged into the GAP. CBRS could be a module that gets plugged into the GAP, Wi-Fi, remote OLT. So a lot of these are technologies that we deploy today in discrete components. Mm-hmm. And so, the list could go on, right? I mean, you could have a compute module, or you could have, if you need some sort of field aggregation module, you could have an Ethernet aggregation module as well. So these are some of the low-hanging fruit that we see.
Okay, great. So over to Elad from Silicom. So what are we going to gain with GAP? What are some of the things you can do with a GAP node that you can't do with today's nodes?
First of all, what you're going to gain is openness. It's fully modular, so you're looking at something which is just like the Lego approach, meaning you can pick your pieces, they all fit together, they have to fit together, that's what's beautiful about it, and you can pick and choose if it's to debug, if it's to progress with technology, as Matt said, or if it's just to add another element that you were missing during the growth of your business. So you can start with something which is completely empty and start building it up and scaling up.
Okay, all right, great. So George, let's go over to you. Maybe you could walk us through a little bit of the sort of the internal architecture. How does the GAP enclosure accommodate cooling that we're going to need for some of today's kind of high-powered electronics?
So part of the struggles with this project is thermal, right? You have to put a lot of stuff in this box, and there's techniques to cool it, both in the lid and base, that are really important. Getting a balance on both sides, the lid and base, is pivotal in getting the thermal dynamics of this right. And it causes us to really look at where the actual pieces are placed inside the node, and it's important to maintain that. And what's great about this is the heat in the thermal dissipation is a struggle, but it opens the door for us, for the market to say, hey, if I have this Lego approach, I'm going to be adding pieces and taking pieces out, and we always have to look at what thermals are going to be there. What's the power dissipation of each of these modules? But it's going to force innovation. It's going to force many folks in the industry who want to play in this arena to design smaller, to design with less power, to design a little more efficiently, to make those Lego pieces part of that infrastructure. And but it's a struggle to do it and maintain it, but it's also, I think, it opens the door for innovation.
And so what is the wattage that GAP is specified?
We're trying to hit that 200 watt
200
number,
watts.
and that 200 watt can easily be brought up. You know, once you plug all these pieces in, you can easily get to 200 quickly, but you need to maintain that. That's, you have the thermal mass of the node to cool it down, and it's going to limit you what you can plug in. You can Lego pieces in and you can Lego pieces out, but it is a limiter, but it's also, like I said, it's a
Right. So
open
for operators who maybe can't drive that much power into a node, I'm not talking about thermals, but power, then they would just scale it back, right?
scale
to
back.
whatever, 160 or whatever they can
yeah,
target that.
as they need it.
Okay. And Jay, I'm going to throw one over to you. So is it feasible, 200 watts?
Yep, it's feasible.
Okay. Simple, confident answer. All right, good.
Check the box.
Toughest question of the night.
So back to Elad. So a lot of goodness, obviously, in modularity, and the whole Lego blocks. But I've had questions myself. I'm sure others have. Doesn't modularity add a lot of cost to a platform?
In this case, not at all. Not only doesn't it add cost, but we've done the calculations. It's minute at best. The backplane is both passive and active. You can use whatever you want to use and not use the other pieces, and it's minute compared to all the other pieces that we have. We have FPGAs, we have compute boards in here, $2-3 at best, so it's not really that significant.
So it kind of comes down to a couple extra connectors, maybe?
Yes, exactly, and not only that, you can depop them. Let's say in your first step you're saying, no, I'm going to go all passive. Don't put in the actives. That's it. It's the same backplane.
Okay. Okay. Well, and I know for the prototype we landed on some basic off-the-shelf type connectors, right? Not super high-priced.
Nothing is high-priced. Nothing is customized. It's all off-the-shelf standard pieces. Again, the idea is to make it commodity, to make other people be able to join us very quickly. Whether if they're building the actual hardware or if they're designing software to that hardware, need to test that software. We're doing everything we can to open the door to as many participants as we can, from the VNFs to the actual hardware manufacturers.
Okay. So Jay, what about the base side, the RF modularity, like let's say versus a tray solution as an example?
So good point, and definitely worth addressing, because I would think some of the immediate term use cases for GAP will be RPD or remote MAC based. So the RF section of the node will become of the GAP platform will become a very important element. We've run the numbers, and from what we can see, a fully loaded platform with RPD application module, all 4 RF modules in the platform, and I mean there's a single-digit premium over a tray. That's for sure. But the modularity brings a lot of advantages. Number one is in situations where node ports, all 4 node ports aren't utilized, you remove one module and you're on a equal cost basis with the tray platform. Number 2 is it allows you to separate the AC and the RF distribution within the platform, which is valuable. And then number 3, just simply from a maintenance standpoint, of one port of your node goes down, you can address that and plug in a new module. You don't have to remove an entire tray to perform an upgrade, and which is obviously disruptive to customers. So.
Okay, great. So a slight cost adder, but not a deal breaker. From just kind of net that out, right?
Got to ask Matt that question.
Okay, well, let me switch gears a little bit. Sean, let's start with you, and then others, if others want to chime in on this one as well. From a vendor perspective, from your perspective, is GAP more of a threat or an opportunity?
I think it's clearly an opportunity, to be sure. First of all, before I go into explaining my position on this, is I want to thank all the collaborators here on the on the panel for putting together the demos and actually showing the reality of this technology. Swing by our booth and all our other partners here. Swing by their booth and take a look at it. It is really, really, really cool stuff, and it is true innovation in demonstration form. So. The opportunities here are immense. Obviously, a platform which can, house a general purpose compute device can run practically any workload. Now, the optionality that comes along with it in terms of running those workloads are down to the operator and what they want to choose to put into the network. The flexibility of the access technologies in and of themselves. So there are some really, really powerful benefits that come along with this, and we think the opportunity is immense. It also allows vendors to really pick their spot and to make the investments that they need to around the areas where they can create competitive differentiation and bring the most value to our customer community.
And Elad, not to speak on your behalf, but I know Silicom has a lot of expertise in compute boards, and you were able to very quickly bring that expertise into our prototype, right?
Yeah, definitely. I think we see the ease of use and the ease of design for such a platform, not only going to next generations of Intel very quickly and very easily, but also offering more and more interconnect between the pieces. If you've got FPGAs, which are moving very fast. I think Sean's point is very important. Time to market is shortened considerably. You're talking about software that could be uploaded to a device immediately. So instead of going through the whole 9 yards, you have a very short cycle. You program, you set it up, and you're ready to go.
Yeah, absolutely. And actually, the prototype demonstrated that very well, because some of the things we were able to do, first of all, the final integration of the prototype was a total of 10 days. So it was 10 days from the time that we had actual hardware, on the compute side anyway, until the show. But the teams were able to start way ahead of that because they were able to use servers and labs that represented that compute platform to get some of the other software components and together and all that sort of thing. So from my perspective as well, time to market, shortening that time to market is just a tremendous, tremendous opportunity. And then I think the fact that we've got five different companies contributing their core competencies, and just their core competencies, so again, not to speak for you, Elad, but I would venture to say if you had to build a node housing, that in addition to a compute module, this probably would not have come together quite as quickly as it all did.
Well, right? you want to use the best pieces and the best partners for each part. Silicom is very good in the design and very good in options of different components, but there are experts like ATX and AOI to do a lot of the enclosures, a lot of the power, the design of the entire build together. So why would I try and reinvent the wheel when there are people who've been doing this for over 20 years?
Right, right. So Matt, what about opportunities for someone to play the integrator role? How do you see that changing?
Yeah, I think integration is going to be a bit of a challenge, but with that, there's going to be more opportunity out there, maybe a third party to help facilitate that, or maybe an existing standard body out there to help facilitate some of the testing on the integration. So yeah, I think it's more of a new opportunity for new entrants.
Okay, great. So maybe a final question. I don't know if I see Roger or Kevin out in the audience.
He's right there.
There he is. So when is the specification going to be done?
There you go.
The specification is ongoing right now. We started earlier this year with a group of about 25 contributors. We're looking for anybody else in the industry that has an interesting gap. But we're really looking to finish the specification for Q1 of next year.
Okay, great. Great, and again, the prototype that we built obviously was in advance of that specification being complete, but we wanted to learn from that experience, and we did. I know I learned a lot, and I think we were able to, I hate the term fail fast, we were able to succeed fast.
And it works.
And it works, exactly. So let me go back here. before I tell you where to go see this, I want to walk through the components again and just fill you in on who supplied those components. Again, just highlighting the multi-vendor aspect of this. So first of all, there's the modular node housing itself. That design was supplied by ATX. And actually, one of our engineers at Intel worked with ATX to modify the lid side to accommodate our components on the lid side. The RF modules, the power supplies, again, supplied by ATX. We had the PCI Express backplane module and the compute module, which were designed and built by Silicom. We have the RPD module, which was built by AOI. And then we have a core, an actual VCMTS core from Cisco, software stack, running on the Intel Xeon D platform. Now, so where can you go see this? 3 different places. We have a complete unit at the ATX booth 1601. So feel free to drop by there, and there's actual traffic running through this thing. We have the lid half at the Cisco booth. We were a little short on bases, so we powered it through other means. But we have the lid half, again, fully functional, at the Cisco booth. And we, Intel, in our meeting room, have a non-functional complete unit. So feel free to stop by one of those areas to go and actually see one of these units. And if you haven't joined yet, please join the effort to complete the spec for GAP. It's not too late, right? We have progressed it quite a ways, but it's not too late to sort of join the effort. So with that, we do have a few minutes, so I think we can open it up for Q&A.
Oh, hi guys, Jeff Baumgartner with Light Reading. I just had a quick question on, I know we've talked about GAP before, or I have with a number of you, but can I get like an update too on cable operator interest and participation? You know, obviously it's good that, you know, Charter's very heavily involved in kind of championing this, but give us an update on who else is kind of jumping in with both feet.
Yeah, I don't know if Matt, if you can take that one, or if I can.
Yeah, go ahead.
No, so I mean, we've had interest from other operators. They are actually part of the working group. Gosh, I guess the way I would characterize it is I would invite them to become more active. I'd love that. But I get the sense that folks are kind of in a wait-and-see mode, or were in a wait-and-see mode. And you know, hopefully once they see the prototype and realize that, oh yeah, this is achievable, I'm hoping that we get some more active participation there from others. But we've certainly talked to several operators who have expressed interest in GAP, but I think they've just been in that wait-and-see mode.
Sounds like you're hiring. Any other questions in the audience?
Hi, Tim Casto with Lanner Electronics. Just wondering about the Intel Xeon D. Is that the initial D1500 family or the new 2100? How many cores? Are you anticipating any use of virtualization technologies in this application or not?
Good question. So what we're running in the prototype is a Xeon D 15. I don't remember the number. It's a Broadwell generation 12-core processor, and it's pretty amazing because the Cisco core is running containers, Kubernetes containers on top of VMware. So we have VMware ESXi running on that, as well as the container environment. So 12-core Broadwell generation Xeon D.
Hi, Fred Dawson, Screenplays. Following up on Jeff's question, I'm interested in knowing how this gets implemented, assuming whether it's just Charter or many operators. How, Matt, are you going to be putting this out there? What justifies replacing your legacy nodes, going to the cost of putting this in? How does that evolve?
Yeah, you know, as we go and deploy new technologies, you know, we're going to be deploying DAA type technologies out in the field. That's going to require a new platform in order to host that, whether it's an RPD module or a MAC-PHY module. And so it's more or less cap and grow style as we drive DAA out there. And so as we're driving that new technology out there, we want to be driving that on top of this platform.
Hi, Marco from ABB Technical Marketing. When you look at the nodes from a historical perspective, could you talk about the thermal challenges?
Sure, I could take that. I mean, I think a lot of the legacy node platforms that exist in today's networks, they weren't designed to dissipate the amount of power that we're now consuming. Definitely, they are significantly less than the 200-watt target that we're talking about for GAP. Is that?
Yeah, and one of the ways that GAP is addressing that is basically the orientation of the modules, especially on the lid side, right? So you saw that backplane. Essentially what happens is the modules plug into the backplane, and they have plenty of area underneath to contact the housing. So that's the critical part. You need to come in contact with, essentially, with your cooling solution, which is the actual hunk of metal, right? And so you can put your hot components on the back side of your module, and then they have an opportunity to contact with the actual housing itself. So I think that's one of the things. Yeah, I don't know if it's totally unique, but it's fairly unique to GAP.
Externally, what's important is the fin design associated with the housing, and lot of permutations and combinations and thermal modeling go into optimization of that. And that's a lot of the secret sauce, and being able to dissipate those levels.
When you
of power.
look at something like the power supply, you could say that a higher efficient power supply will yield a help for thermals. Anything else electrically going on within the node that has evolved for the help toward the thermal load?
Sure. I mean, we're always driving efficiencies in power supplies. Another interesting piece of technology that's started to rear its head is called digital pre-distortion, which allows you to bias hybrid amplifiers at lower current levels, which every bit of it helps. Sean, you have anything to add?
Yeah, and I would say, as it relates to general compute modules, optimizing the code structure to, turn off cores, to flex memory utilization and footprint, and that would be value add in the compute modules themselves to really take that footprint down to a, reasonable level to basically fit inside the thermal envelope.
Thank you.
Okay, I think we have time for maybe one more. Anyone? Any last comments from the panel? No? Okay. Okay, great. With that, please join me thanking the panel for the session today.
Thanks, Ed. That was a great, very popular panel. Anyway, thank you all for joining us. Back here in about 10 or 12 minutes with a fascinating take on the many approaches to virtualization.